Hi, I'm Elizabeth Chang-Davidson, and I will be presenting alternative scan strategies for laser powder bed additive manufacturing to expand process space. I am a PhD student in Professor Jack Youth's additive manufacturing group at Carnegie Mellon University. So this work was done in conjunction with Nicholas Jones and my advisor, Professor Jack Youth. You can contact me at my email address here with any further questions. So to start off with, I want to give an overview of what I'll be covering in this presentation. I'm going to start by giving some background on what existing scan strategies exist in additive manufacturing, specifically in laser powder bed fusion. Then I'm going to move into defining this new strategy that I'm talking about and talk about what the key applications of it are, such as creating unusually large melt pools. These large melt pools are going to result in larger grains, and larger grains are going to result in higher ductility in built parts. In addition, these very large melt pools are similar to the lens process, but can be built using a laser powder bed fusion machine, meaning that you can mimic those build parameters and get a much wider variety of results from a laser powder bed fusion machine. Finally, there's an interesting property where you can get these unusual wobbly melt pools, as opposed to the typical steady state melt pool, which has the same size and shape throughout the build process. Next, I'll talk about how to use this new strategy and how to select process parameters. And then finally, I'm going to show some experimental results of testing this new strategy. So to start off with, in laser powder bed fusion, the typical strategy is rastering, so going back and forth across the part at a fixed hatch spacing with a contour pass at the end to cover the edges of the part. There are some variations that machine manufacturers have come up with, notably stripes, in which you divide the part into these different stripes and raster within those stripes specifically. Here you can see a video of one of the machines rastering back and forth. In this video, you can't actually see the laser moving back and forth because it moves faster than the camera can capture. And so it appears to be a horizontal bar of light moving up and down the part, when it's actually just moving back and forth very rapidly. So when that laser is moving back and forth, if you were to zoom in, you would see a characteristic teardrop shaped melt pool. So what I've shown here on the left is a cross-sectional view of that teardrop shape with many of the key melt pool dimensions labeled. So in terms of melt pool size, the two key dimensions to take note of are melt pool cross-sectional area in pink here and melt pool width in orange. So these two measures of melt pool size are closely correlated with each other, and in addition have been correlated in the literature to grain size, which is of course closely related to material properties. In the top right corner here, you can see an image from NARA 2017, where a part was printed with 3 different process parameters in different parts of the build, and you can see that visible donut shape is where different process parameters were used, resulting in a visibly different grain size. So in order to understand these melt pool dimensions, it's useful to plot them on a process map. So on the right here, you can see an idealized process map where lines of melt pool size are drawn. So they're actually quite close to linear in practice. In the bottom right corner, they result in smaller melt pools. In the top left corner, they are larger melt pools, with this generally increasing trend as you move to the top left. So you can plot, in addition, on the process map, areas of good process parameters and flawed process parameters. Flawed as in resulting in porosity in the build part. So you can see that there's only a very narrow good region here, and that's going to limit how much variation you can get for this process in melt pool sizes. On the top left side, you're limited by keyholing behavior. Keyholing is a phenomenon that occurs at high powers and low velocities. It results from vaporization under the laser resulting in a channel of vaporized metal in the melt pool, which allows the laser to bounce around, increasing the effective absorptivity of the material. So this cavity is also going to result in very characteristic deep melt pools. Keyholing is controlled by the ratio between the melt pool width, or the melt pool size, and the beam diameter. For most laser powder bed fusion machines, the beam diameter is fixed, which means that this keyholing boundary is a fixed property of the machine. The goal here is to move into this red region without generating keyholing flaws, so as to increase process flexibility. The lens process can operate in this region because lens machines have a different characteristic beam diameter. And as we mentioned, keyholing is controlled by the ratio between melt pool width and beam diameter. So now that we understand more about the background of our typical strategies, let's dive into what our alternative strategy is in detail. So the proposed strategy here is to take the stripes phenomenon from before and make the stripes much, much narrower than typical. So what that's going to create is a single very large continuous melt pool. If we take a look at the video from before, we can remember the glowing blob that we saw moving. Our goal is to make it so that that glowing blob is in actuality the melt pool as it moves across the part. So on the right here, we have a top view of a sample melt pool in orange with the nominal stripe boundaries shown in black. So we have a variety of key variables that we want to explain. So the laser power is shown here approximately where the laser spot would be on the melt pool. Laser velocity is shown along the raster pattern that the laser travels. We have melt pool velocity moving upwards, which is also the stripe velocity. So the key takeaway here is that the melt pool velocity and the laser velocity are no longer the same. Previously, in the characteristic teardrop shape I showed, those two were one and the same, but in this new strategy, they are now perpendicular and also not equal in magnitude. We also have the geometric parameters for the hatch spacing here and the stripe width, which govern the exact pattern that the laser travels, as well as the turnaround time at the end of each raster. So in order to relate some of our key process variables, we can define a governing equation from simple geometric relationships. So what we can do is take melt pool velocity and break that down by its definition. So velocity is distance divided by time. So the distance it travels is one hatch spacing upwards in our diagram. And the amount of time it takes to travel that distance is going to be the amount of time it takes to traverse across the stripe width and then turn around and move to the next raster. So the amount of time it takes to traverse across the stripe width is W divided by V lays. The amount of time it takes to move to the next hatch spacing is the turnaround time. So once we have this strategy set up, we need to model it to understand it. So there are a couple of different approaches we could take. One of them is finite element modeling, which I'm sure many of you are familiar with. Finite element modeling is accurate and it can incorporate complex heat transfer effects. However, it runs very slowly and it requires careful meshing and time stepping in order to generate accurate results. An alternative here would be using semi-analytical models. So this model is conduction only, but it has been shown to capture a majority of the heat transfer effects in most cases. It's significantly faster than finite element modeling, and in addition, it can be evaluated at specific times and locations instead of needing to run an entire simulation to figure out what happens at the end. So the program I'm using for this research was written by Nicholas Jones, one of my lab mates, and uses the Egertei semi-analytical model. So now that we have these simulations, we need to analyze their output. So the results of the simulation span a whole spectrum from the left here to the right of different characteristics, shapes, and behaviors. So if we look at the left view here, we characterize this as a continuous melt pool because we can see that it is moving upwards roughly continuously. We don't see a lot of remelting or wobbling going on. Conversely, on the right, which we characterize as non-continuous, is essentially all of the melt pool is getting remelted as the melt pool travels back. So if you think about it from a materials perspective, it's getting solidified and remelted, as opposed to only experiencing one melting and solidifying event. Also, on the right-hand side, all of the melt pool solidification velocity directions are horizontal as opposed to vertical from our top-down view. So we get essentially the same outcome as our traditional scan strategy on the right, and the melt pool sizes are not increasing. So on the left here, we get a much larger melt pool than we would in our traditional scan strategy, and we get that the melt pool is moving upwards instead of left to right. In the middle, we have this interesting intermediate case. So some of the melt pool within the red lines is behaving the same way as it does on the left. It's not remelting, it's moving vertically upwards. Some of the melt pool outside the red lines is moving left to right and is continuously remelting and solidifying. So what we can do is look at the ratio between the red width, which is the width over which it is moving upwards, and the nominal stripe width shown in black. And we can use that number as our simulation output. So on the left, we get 100% as that number. On the right, we get 0%. And in the middle, we get about 2/3. So now that we have the ability to characterize our simulation outputs, let's look at what the effects of different parameters are on those simulation outputs and develop a method for selecting useful process parameters. So as the default behavior and if our traditional scan strategy is non-continuous, what we're going to look at is what level of each variable is going to increase continuity in the melt pool. So first of all, power and laser velocity produce somewhat more complex effects, and we're going to look at those a bit later. Hatch spacing, we can think of small hatch spacing is going to make the laser go back and forth over the same area repeatedly, which is going to result in more continual melting. So the other thing it affects is you'd want to maximize your hatch spacing in order to maximize the velocity of the melt pool. Higher melt pool velocity is going to result in higher build rates, which is desirable. Finally, simulations show that hatch spacing has a very large effect on how continuous the melt pools are. We can also look at melt pool forward velocity as one of our variables, which we want to maximize for our build rate. We can look at stripe width. So if you imagine an infinitely wide stripe, that is definitely not going to be continuous. It's going to be essentially the same as our traditional scan strategy. So we see that we want narrow stripe widths to generate more continuous melt pools. However, simulations show that stripe width, as long as it's small enough, does not have a strong effect on how continuous the melt pool is. Finally, turnaround time is directly the amount of time that the melt pool has to cool between laser rasters. So a smaller turnaround time is going to increase continuity. So what we're going to do in order to study these many different variables is we're going to study some, derive one, fix two. So we're going to fix our turnaround time at the minimum turnaround time that the machine is capable of. We're going to fix the stripe width at a reasonable value within the range of values initially studied. We're going to derive the melt pool forward velocity using our geometric relationship. And then we're going to study the three remaining variables: laser power, laser velocity, and hatch spacing. So in order to study three different variables, it's helpful to plot it as several different two-dimensional spaces within a three-dimensional space. So if we fix our hatch spacing at a specific value, we can plot across power velocity space what regions produce continuous melt pools, wobbly melt pools, or non-continuous melt pools. In general, the upper left of this region is going to be continuous, the lower on the right is going to be non-continuous, and the boundary between those two is going to be wobbly. So as we increase our hatch spacing, we see that this boundary moves up and to the left. And if we look at this from the perspective of a specific power velocity combination circled here, we can see that at small hatch spacings, it's continuous. At an intermediate hatch spacing, it's wobbly. And then finally, at very large hatch spacing, it's going to be non-continuous. So we see a spectrum from small to large hatch spacings, continuous to non-continuous. So we want to select some parameters to study experimentally to verify our simulations. So we've selected these points shown here in red in power velocity space. At each power velocity combination, we use our simulations, as in the previous slide, to figure out where that transition region between continuous and non-continuous is, and try to select a hatch spacing smaller than the transition and larger than the transition to bound that region. So let's take a look at the results of running those experiments. So at each of these red points, we have two different hatch spacings with a top-down image of the melt pool result shown here. So the end of the melt pool shows the final melt pool shape as it solidifies. And we have 16 points here. Overall, the results are more continuous than expected from simulations. Let's take a closer look at one pair of these experiments at a single power velocity combination, this one specifically. So this is 350 watts and 100 millimeters per second, and the two hatch spacings are 150 microns and 350 microns. So on the left side, we have the smaller hatch spacing, and what we see is a very continuous melt pool. There's not disruptions along the length. It's pretty much the same as you go upwards. On the right side, we see that there is a significant amount of disruption at the frequency of the hatch spacing. We can see some of the same ripples as you see in the left down the middle of our melt pool. But on the left and right sides of our melt pool, we can zoom in a little and see that our ripples are perpendicular to each other. These ripples are generated by the melt pool moving forwards. So we can see that from this close-up view that we have perpendicular lines here. And what this means is that our melt pool is remelting over an old melt pool, which is showing us evidence of the wobbling behavior we observed in simulations. So we had selected this left-hand set of parameters to be continuous and the right-hand to be non-continuous. However, we can see from our melt pool trace that what actually happened is the left one was continuous and the right one was wobbly. So we're seeing more continuity than we expected, but we are seeing that a larger hatch spacing is more wobbly. So in general, this trend held across all of the experimental points, where they were more continuous than expected, but kept up this trend where a larger hatch spacing meant more wobbliness. So the reason why we would see this discrepancy between simulation and experiments is this keyholing phenomenon we discussed. Because keyholing increases our effective absorptivity, more power absorbed means bigger melt pools than we expected. And we can see evidence of keyholing in the extreme depths of some of the melt pools. On the right, you can see an example of that. You can also see visible keyholing porosity there. So the question is, how do we get around this running into keyholing even when we use our new parameter set? So keyholing occurs at different severities across our samples. Severity of keyholing can be measured by how deep the melt pool is relative to the expected depths from our conduction-only models. If we carefully calibrate our hatch spacings, what we can do is avoid this keyholing behavior by being just over the threshold to get continuity in our melt pools. We can see in our left-hand sample here that the melt pool is relatively shallow and broad, whereas on the right hand, we see some pretty extreme depths compared to what you would expect from our conduction models. Our conduction models predict a broad, shallow melt pool resulting from this strategy. So in conclusion, what we've shown here is that we can generate very large melt pools from the scan strategy, which is going to increase our process flexibility. These large melt pools mean large grain sizes, which will result in ductile material properties. So we're also seeing a sort of new and different melt pool behavior in these dynamic wobbly melt pools instead of our typical steady state melt pool that's the same shape and size. This strategy shows promise to be a bridge between the lens and the laser powder bed fusion process to generate intermediate intermediate melt pool sizes, or to mimic the lens process in a different machine. For future work, there's more work to be done in determining the process space boundaries for keyholing and for finding the boundary between continuity and non-continuity. And finally, to print an entire part using this strategy in order to fully verify the material property relationship. Thank you for listening to my talk. I have acknowledgements for the many people who helped me in this project, and I have references for many of the concepts discussed. Thank you.